So scientific notation essentially says I can write something as 3.14 into 10 power 0, or I can write 1.024 into 10 power 3, or I can write 2.5 into 10 power minus 15. All of these, the interesting thing is, okay, let me just, this part over here is using the same number of digits, right? And this essentially is my exponent, which is another word for the scaling factor that I had for fixed point numbers. What's the main difference? In fixed point numbers, I gave you a notation. I told you that I am using 4.4. And the moment I say 4.4, it means all numbers with 4.4 have a scaling factor of 2 power minus 4. But in scientific notation, every number carries its scale factor along with it. So 3.14 into 10 power 0, that number is carrying a scale factor of 0 along with it. 1.02 into 10 power 3 is carrying a scale factor of 10 power 3. 2.50 into 10 power minus 15 is carrying a scale factor of 10 power minus 15. Okay, so each number basically carries its own scale factor along with it. Okay, how do we make use of that? If you think about what I have done over here, I have basically said, look, I will use some 3 digits in order to represent the value, the actual sort of precision of the number, and I will use some additional digits 0, 3, minus 15, etc. in order to represent what my exponent is supposed to be. Okay, I am just going to separate those out. Okay, so what was proposed in order to do the same thing for binary was to say, let's say that I have a 32-bit range of values. Okay, let me divide this and say I will have my exponent over here, and the remaining part, which is the actual value, I call it the mantissa. And the one choice that was made in this case was to basically say I will use 23 bits to store the mantissa, 8 bits to store the exponent, and 1 bit for the sign. So here what we say is the mantissa, I will assume, always has a 1 in front of it, followed by 23 bits of mantissa. Okay, so basically it becomes a 24-bit value into 2 to the power of, not 10 to the power of, but 2 to the power of this E that I have over here. But as one added twist, which is not easy to justify but makes sense when you actually go into the development of this notation, they just do E minus 127, where this is treated as a unsigned 8-bit integer. Okay, what is an unsigned 8-bit integer? It just means it has values in the range 0 up to 255, 0 up to 2 power 8 minus 1. So E is a number in the range 0 to 255. I take that, subtract 127. So in other words, E is not using 2's complement, E is just an unsigned integer. I am then going to subtract 127 in order to get the actual value that it has. That's not exactly the same as using 2's complement, right? Look at the numbers, you will realize that it's actually something else called a base offset arithmetic, but it gives you the same range of values, right? You are not going to lose anything over there. What happens over here, this 1.mmm, the maximum value, or rather the minimum value that I can have over here is 1.000 is equal to 1, and the max value is going to be equal to 1.111, which is 2 minus 2 power minus 23, which is approximately equal to 2, okay, it's some 1.99 something. Now, what this means is I have got a 32-bit value similar to my 32-bit integers, but now I have got a 32-bit value. What am I going to do with it? I want to find out, I know that I can represent numbers using this format. Okay, an example number would be something like 0, 0, whatever, and something of this sort, right? This would be exponent, this would be mantissa, and this is the sign. Okay, so this value is going to be equal to 1.01, sorry, 1.10100 into 2 power 106 minus 127, okay, or in other words some whatever 1.5 something into 2 power minus 21, which is approximately equal to 1.5 into 10 power minus 7. Okay. So, if I had a number like this, this is how I would interpret it. Okay. What impact does this have on the dynamic range? Now, let us look at the dynamic range, right. The interesting thing to keep in mind is this mantissa now has nothing to do with the dynamic range. It has very little influence on the dynamic range because the mantissa at most has a dynamic range of 2. It can go from 1 up to 2. Okay, so it can't have a significant influence on the final dynamic range. But what it does is it allows you to give precision, 4.50, 4.501, 4.5013, right? Those kind of digits, the extra digits can be represented in the mantissa. The exponent takes care of the dynamic range. How does it do it? Smallest positive value corresponds to sign equal to 0 because it is positive, exponent equal to, I want the smallest value, therefore exponent equal to 1, right. I am going to say 0 is reserved for another purpose. So, I am not going to allow 0. If I do not allow 0, the smallest exponent I can have is 1, okay, which basically corresponds to 2 power 1 minus 127 equal to 2 power minus 126, and this also corresponds to an m equal to 0, which means the actual value is 1.0 into 2 power minus 126. Okay. What is the largest positive value? Again s is equal to 0, this is a sign bit. E in this case is again, it should be 255, but once again 255 is reserved, I will say 254 is permitted, which means that it basically corresponds to 2 power 254 minus 127 is equal to 2 power plus 127, okay. And the mantissa in this case is all ones, which basically corresponds to a value of 1.999 something into 2 power plus 127. Okay. 2 power minus 126 is approximately equal to 10 power minus 40, somewhere around that. Right, and this is approximately equal to again 2 power plus 128, once again somewhere around 10 power plus 40, 41, 42, something of that sort. I am just going to write it as 40, it is close enough. Okay. What is my dynamic range? 10 power 80, okay. 32 bits of storage, right. I am using, how much memory am I using in the computer? 32 bits. With those 32 bits, integers or fixed point numbers, the dynamic range that I could get was 10 power 9. The same 32 bits organized in a different way, interpreted in a different way, that is all. The computer does not know what the difference is, it is just storing 32 bits of data. It is up to you or the program you write in order to interpret it differently. You get a dynamic range of 10 power 80. okay, just because you have allocated some space for the exponent, and each number can now carry its own scaling factor along with it. What do you lose? Have you lost anything here? Precision. I now have only 23 bits of mantissa. I had 32 bits earlier, right? 31 bits. That has been reduced. So essentially, whatever I lost, whatever I gained in the exponent, that many bits I have lost for the mantissa. It turns out that even for scientific computations, in most cases, the dynamic range improvement is better than the loss in the precision, or more important. The dynamic range improvement is more important than the loss in precision. Okay. Having said that, what I have described so far is something called single precision floating point. Why floating point versus fixed point? In fixed point, the name itself suggests the decimal point location has been fixed by convention. I just say 4.4 and that's it. You can't really move it anywhere. Whereas floating point, every number carries its own exponent with it. Okay. Single precision basically refers to the fact that this is 32 bits. Okay. And in fact, to be more precise, this is something called the IEEE 754 standard. Okay. It's like I told you, it's a convention. The IEEE, the Institute of Electrical and Electronics Engineers, they have defined this as a standard that everyone can follow. Okay. And once you follow this, it basically says, look, this is exactly the meaning of standard IEEE single precision floating point.